Now let's talk about the relationship between rotational inertia and torque. Remember, we have said that from our previous video, we said that torque can be given by two formulas, and we have derived those two formulas. We said that torque can be given by the force times the perpendicular distance, in this case is the radius. Then again, torque is given by inertia times the angular acceleration. Now this torque and this one is the same, therefore you can set them equal to each other. You can say inertia times angular acceleration is equal to the force times r. Now this is very important. Okay, now I have got some questions and the same relationship between rotational inertia and torque. So the first question is this question is from one of the exam past papers. So it's saying a merry-go-round has a mass of 100 kg and radius of 1.6 meters. Consider it as a uniform disk of a moment of inertia of equal to half mr squared. A man pushes with a horizontal force of 80 newton tangentially to the merry-go-round. But one which is saying, so this question had 10 marks. So what is the angular acceleration produced? At 2, starting from rest, how fast will the merry-go-round be moving? That is in revolution per second after 12 seconds. How many revolution, that is part 3, how many revolution would the merry-go-round have made in 12 seconds? So let's start with part A. Part A is asking about the angular acceleration. Now, from the relationship which I've just come up with here, which is the torque is equal to force times r, again torque is given by inertia times the angular acceleration. I can use that to find the angular acceleration. Okay, so from our data we can clearly see that we have the mass to be 100 kg, our radius is 1.6 meters, our inertia we have been told that is half mr squared. What else? The force is 80 newton. So the question is, what is the angular acceleration produced? So I can use this formula to find my angular acceleration. Now what I can do at this point, I know that inertia is given by half mr squared. I can replace this with what I have. So I'll say inertia, I'll replace it with half mr squared times angular acceleration is equal to the force times r. Now, sometimes if you are confused with what I'm doing here, the best way you can do is you can find inertia alone separately using that formula, and then you just plug in direct. That is just okay. So what I'm doing here is I'm just replacing where there is inertia with a half mr squared. But it's okay. You can find the inertia, plug in the mass, the radius, then square it. That is going to be the inertia. Plug in the inertia there, divide both sides by inertia. That is going to be your angular acceleration. Okay, so you should try that, then you're going to see that the answer is going to be the same. Now for me to get rid of the half, I can divide, or I can do times 2 everywhere. So 2 and half is going to be cancelled. I have m r squared alpha is equal to f. I have 2 fr. But I can also see that I can divide both sides by m r squared, even here by m r squared. So these two can cancel. Then here again, this and 1 r will cancel, I'll remain with 1 r. So alpha will be equal to 2 f divided by m r. Let's try to plug in the values. Our alpha will be 2 times 80 divided by the mass is 100 times the radius is 1.6. So we expect our angular acceleration to be 2 times 80 is 160. I'll put 160 here. I divide everything by 100 times 1.6 is also 160. Okay, so now if I divide 160 divided by 160, I'll get 1 lad per second squared. So that is my angular acceleration. Now part B is asking us, now I can get rid of this. Okay, part B is asking us to find is saying starting from rest, meaning that the angular acceleration in that case, because it is starting from rest, is 0 lad per second. Starting from rest, how fast will the merry-go-round be moving in revolution per second after 12 seconds? And we have been told that the time now is 12 seconds. Using those three formulas, we have the first formula which we have to know: the final angular velocity is equal to the initial angular velocity plus angular acceleration times time. Another formula which we need to know is that the theta is equal to the omega initial times time. Okay, then plus, okay, plus half angular acceleration times t squared. Another one is the omega final squared is equal to omega initial squared plus 2 alpha theta. Now, using these formulas from the data which we have, which formula is going to help us to find the final angular velocity? I believe the first formula can work. I can't use the second formula because there is no final angular velocity, so I can't use this. I can use this, but I don't have the theta in this case, so I can't use that. The only formula I can use is the first formula. Okay, now the first formula is this is equal to that. I'll shift initial to the other side. I'll have the final minus initial is equal to alpha t. Let's divide both sides by t, both sides by oh, we are trying to find the final. Sorry, we are trying to find the final, and we have the time. Let's just plug in dialect. So the final will be, the initial is 0, this has to be plus, so plus acceleration is 1 times the time is 12, so the final will be 12 lad per second. But the question is, we need to leave the answer in revolution per second, so we have to convert this from lad to revolution per second. What we should know is that in one revolution there is 360 degrees. At the same time, there is 2 pi lad. So I can use this to convert whatever I want to convert. Now I have 12 lads. I'll set the units in such a way that they should cancel each other. So I'll say in 2 pi lad there is 1 revolution, because we're saying that 1 revolution there is 2 pi lad. At this point we can see that lad and lad can cancel. Now I'll have 12 divided by 2 pi. So 12 divided by 2 pi, which is giving me 1.91. So my angular final will be 1.91. 9 is 1.9098. I'm just rounding off to say 1.91 revolution per second. Now, because seconds seconds is seconds, unless if it was unless if we were told to say we need to find the answer in revolution per second. Now, using dimension analysis, the best way you can do is this. You say in two, you have got 12 rad per second. So you say in one revolution is equal to 2 pi rad, which is the same. So second, you put them down there. Okay, so that is it for question 2. Let's now go to part 3, which is saying, let's just put the final here. The final is in rad is 12. Okay, then they want us to find the revolution anyway. Now I can get rid of this. So how many revolutions would the merry-go-round have made in 12 seconds? Okay, whenever you see a question which is asking about revolution, just know that they are asking about the theta. Always, if they're asking about revolution, they're asking about the theta, meaning that I can use the second equation because I have the time, I have the angular acceleration. I can also use the final, or the third equation, because I have the final and I have the initial. Okay, so let me use this one, but you can also use this one. You'll be able to find the same answer. So I'll use the final initial squared plus 2 alpha theta. Let's shift this initial to the other side. It will be minus initial squared is equal to 2 alpha theta. We want to find theta. We divide both sides by 2 alpha, even here by 2 alpha. So we can see that this will cancel. So our theta will be equal to final squared initial divided by 2 alpha. Let's plug in the values. So we plug in the values. We are going to have theta to be equal to, I'm going to have the final is now 12. Now I have to square it. Initial is 0. I square it, divided by 2, acceleration is 1. So theta will be equal to 12 squared minus 0 divided by 2 times 1, which is just 2. So it's 72. So this is 72 rad. Okay, 72 rad. Now the question is how many revolutions? So we need to convert this one now to rad. Okay, so converting this to rad, we can clearly see that we're going to have theta to be equal to, let me just do this, I convert it direct, it will be 72 rad times, in one revolution I'll set the unit in such a way that they should cancel each other. There is 2 pi rad and rad will cancel. I'll divide 72 by 2 pi, so I'm getting my theta now in revolution to be 11.459, which is the same as 56 revolution. As simple as that. Now you can also use the second formula to find that, and you can say that you're going to have the initial, the theta to be equal to, you can also use this formula. So theta, the initial is 0, so this one is going to be cancelled because the initial is 0. So have half, then the angular acceleration is 1, the time is 12, we square it. Alpha will be 12 squared is 144. 144 divided by 2 is 72 lad. So you convert this to revolution, you find the same answer. So that is it for this question. But I have another question here, which is also relationship between the inertia and the angular, the rotational inertia and what? So we're talking about rotational inertia and torque. Okay, so the relationship which is there, we can see that torque is helping us to come up with the initial formula. So another question is saying a wheel of radius 6 centimeters is mounted so as to rotate about the horizontal axis through its center as shown in the figure below. A string of negligible mass wrapped around in a circumference carries a mass of 200 grams attached to its free end. When allowed to fall, the mass descends through 100 centimeters in 5 seconds. Calculate part A, the angular acceleration of the wheel. Then part B, they are saying we should calculate the moment of inertia of the wheel and the tension in the cord. Now, to calculate the tension of the so what I'm going to do here is I have first to come up with a free body diagram. Okay, I can clearly see that it was in free form motion. Therefore, I can see that the tension is pointing upward, but there is a force which is pointing downward, which is the weight force. In this case, it's mg. Now, it was descending. Definitely, it was coming to rest. So the acceleration has to be negative because it was decelerating. Okay. Now, what we should know is that the relationship still starts from here. Torque is given by force. In this case, is the tension force. So tension force, I'll say Ft. Okay. So Ft times R. R is the radius in this case. Okay. Now, from our data here, we can clearly see that we have got the radius, which is 6 centimeters. I'll convert it. I divide by 100. I'll get 0.06 meters. What else? I also have the mass. Okay. The mass, which is the mass of this. Okay. The question is, it carries a mass of 200 grams attached to its free. So this is the guy we're talking about. So I'll put M. Now the mass is 200. I divide by 1000. So 0.2. What else can we see? We have got it descended. Now what we have to remember here is that it started from here. So it's going to descend from this point. Okay. From this point all the way to here. Now this object has got the mass, then there is mg here, so it descends the distance from this point all the way to there. It was about 100 centimeters. In that case, I'll just say d, or h, which is the same as h, is 1 meters. So the distance is 1, which is the same as the height in this case. The time is 5 seconds. Now the question is, calculate the acceleration. Okay. Now what we should know is that torque is also given by inertia times the angular acceleration. So from the previous question, we said that we can say inertia times angular acceleration is equal to the force times r. Now in this case, we don't have the tension force, then we also don't have the inertia. The question is, we need also to find the inertia. Then again, the question is find the angular acceleration. So what we can do now is this. We can, let's see the relationship is going to be there for tension force. I'll say For the tension force, I know that there is a force pointing upward. Okay, that force is the tension force. An object is coming down, the acceleration is definitely negative. The summation of all the forces in y direction, okay, we have got the tension force pointing upward minus mg pointing downward. Now, according to Newton's second law, this is going to be replaced by mass times acceleration. But in this case, acceleration is negative, so I have to say negative ma is equal to the tension force minus mg. I have to shift this to the left hand side, so it's going to be negative ma plus mg, okay, is equal to the tension force. Now I can relate this and say the tension force is equal to, I can start with mg, okay, mg then minus ma. Now I can see that this is the formula I can use to find the tension force, but I don't have the acceleration. But now let's do this again. The question here, but the last question is saying we need to find the tension force. Now I can start with the tension force, then I come to the moment of inertia, okay, and angular acceleration. Once I have the tension, then it's going to be easy. Now I will just start now plugging in the values there, then I find. Okay, so meaning I can first find the last question, I come then to the, if I want I can go now to the second. Now we can't solve this without finding the tension force. That's what I mean. So we need first to to find the tension force. So we need first to find the acceleration. We can find the acceleration because it started from rest. We know the initial velocity. Okay, the initial velocity meaning it was 0. Using, I want to find the acceleration using this formula. D is equal to initial velocity times time plus half acceleration t squared. Because it was coming down, the distance is 1, the v initial is 0, the acceleration is the one we're trying to find, the h is 1, or which is the d, the time we've been told is 5. Now let's go ahead and find the acceleration. Now this is going to be cancelled because the initial acceleration velocity is 0, so it will be d is equal to half at squared. Let's do times 2 everywhere to get rid of half. So it will be 2d is equal to acceleration t squared. We divide both sides by t squared, even here by t squared. So these will cancel. I'll have t, or I want to find acceleration. So I'll have acceleration to be equal to 2d divided by t squared. So acceleration will be 2 times 1 divided by the t is 5, but we square it. So acceleration will be, okay, so the acceleration is going to be 2 times 1, which is just 1. I divide by 5 squared, which is 25. So the acceleration is 0.08. Let me put it here. Acceleration is 0.08 meters per second squared. That is my acceleration. Now I know now the acceleration. I can go ahead and find the tension force. At the same time, I can go ahead and find part 1, which is the angular acceleration. Now I can use this. I know that linear acceleration is given by the angular acceleration times r. Linear velocity is given by angular velocity times r. Linear displacement is given by angular displacement times r. These formulas are very, very, very important. Now, in this formula, I can make, I have the linear acceleration. I can make, now I'm trying to solve part A now, which is part 1. Okay. Now I can get rid of this. So I'm going to say A is equal to alpha times r. I can divide both sides by r. These they will cancel. alpha will be equal to A over R. So A is 0.8, 0.08, R is 0.06. So my alpha, it will be 0.08 divided by 0.06, which is 1.33 Rad per second squared. I'll put it here. So my alpha is 1 point, it's just 1.333, so I can put it in 3 decimal places. Rad per second squared. Now I'm done with that. Now I can go ahead and find the tension force. That is now part 3. So the Ft is equal to, I can factor out m, g minus a. Ft will be, m is 0.2, g is 9.8 minus 0.08. So my Ft will be equal to 9.8 minus 0.08, that is inside the brackets there, then times 0.2. I'm getting my tension force to be 1.944 newtons. Now, using this formula, I also know that I can find the moment of inertia. Okay? Because I have everything now. Now I want to find the moment of inertia. I'll divide both sides by alpha, here by alpha. So inertia will be equal to the tension force. I have the Ft times R divided by alpha. So I'll have the moment of inertia will be equal to, the tension force is 1.944 times the radius is 0.06. I divide this by the alpha is 1.333. Okay, so moment of inertia will be 1.944 times 0.06. I divide this by 1.333. So I'm getting moment of inertia to be 0.0875. Now inertia is mass times r squared. So mass is kgs, the radius is in meter, but it is now squared, so it is kg meter squared. So this is now kg m squared. So this is my moment of inertia. Now I can see that part A is asking about angular acceleration. So the angular acceleration is this one. Part B is asking about the moment of inertia. So the moment of inertia is this one. Part C is asking about the tension in the cord. The tension in the cord is this one. So this is important. We have to know this. We need to know the relationship which is there between the rotational inertia and the torque. And it's going to help us to solve a lot of questions.